So in the previous lecture, we had discussion on Ponchon-Savarette method. So the method based on enthalpy balance and very rigorous balance. And then based on that method, we had couple of examples where we calculated the number of plates, condenser load, boiler load, etc. Today lecture, we take up a new method known as McCabe and Thiele method. All right. This method is actually the approximations. So you have certain assumptions made in this method, but it turns out to be that this method is more popular in the sense that most of the industrial distillation column can be designed, or we can do the calculations for condenser load or the reboiler load or the number of plates, etc., quite with a good reasonably accuracies. In other words, if we apply Ponchon-Savarette methods and we get say number of plates say 20 or 30, then this method will give a very close results, say 31 or 29, etc. All right. So although there is an approximation in this method, but turns out to be that for most of the purposes, this method is a reasonable good working one. All right. So before we get into this mathematical aspect of it, let's try to understand that what assumptions we have in this method. Okay. So if you recall, we made energy balance or enthalpy balance, we made a species balance, and we made a total molar balance. We took a section in enriching section, we took a section in the stripping section, and we made this balance over that envelope. All right. Now if you recall, in this case, in the previous case, the liquid flow rate, it changes, right? So from one plate to another plate, the molar flow rate of the liquid will change. Similarly, vapor which flows from one plate to another plate, the molar flow rate of the vapor will also vary here. All right. What assumption we make here is what we call equimolar overflow and vaporizations. That means we assume that L, the molar flow rate in the enriching section, and L bar, molar flow rate in this stripping sections, remains a constant, right? So L1 to L2 to L3, L4 in one section, and L1, L2, L3 or L bar 1, 2, 3, etc. in the stripping section, they are constant. Similarly, the vapor phase, vapor molar flow rates in both the sections are constant. So physically what happens here, if we have 5 moles of vapor reaching a certain plate, all right, then 1 mole suppose condenses to the liquid phase, then another 1 mole gets vaporized to this vapor phase. So that's the reason. So whatever we have del X change in the molar flow rates of the vapor because of the condensation, it's same as the molar flow rate of the liquid caused by vaporizations. So that results in this assumptions that L in one sections or L bar in this sections or G in one section and G bar in another section remain constant. Okay. So if you make these assumptions based on certain thermodynamic calculations or thermodynamic assumptions, then we will see that there is a much easier method to calculate the number of plates or to do the calculations for condenser as well as a reboiler. So as I said earlier, although this sounds a bit rigorous assumptions, thermodynamically it turns out to be that it's not very far from the reality, one, and that second, it results in a very considerable simplifications calculations, and third, the results which we get, approximated results for number of plates, is not very far from what we get from this Ponchon-Savarette methods. So in other words, if you account for certain efficiencies in the column, etc., then it's possible that we get the two results very close. All right. So we look at this McCabe-Thiele method in this lecture and see where we are making these assumptions and how does this assumption result to the simplifications. All right. So let's start with this McCabe method, McCabe-Thiele method. All right. So we make a note that of course this method has an approximation. So what is the approximation in this method? We assume, or there is an assumption, that assumption of equimolar overflow and vaporization. All right. So we will discuss about this. We are assuming that liquid flow rate, essentially overflow, so from one tray to another tray, the molar flow rate remains constant. Similarly, when we say equimolar vaporizations, then the vapor flow rate, equimolar flow rate of the vapor from one tray to another tray is a constant here. All right. So we will continue with the discussion later. This method is simple, simpler than the previous method, which we had Ponchon, known as Savarit. If you recall this method has a very rigorous calculation for energy balance, or we had this enthalpy balance. All right. In this case, no such enthalpy balance is required for a stage or for stages. So you can see the method is quite simple here, and we don't require any enthalpy balance. All right. Of course, we have some minor calculations for feed tray. So any balance we will do, it's only for the feed tray. So you can see that this method has although very rigorous assumptions as it reads here, but it results in a very considerable simplicity. Okay. So essentially, all the time or most of the times we would be referring to this y versus x equilibrium diagram. So this is the foundation and the basis of your Maccabee-Thiele methods. All right. Unlike in the previous case, Ponchon-Savarit methods, we focus considerably or most of the times on HXY diagram, where we had this HG and HL curve. All right. But in this case, this y versus x diagram for a certain temperature or for a certain pressure holds good. All right. So we have this will suffice. Okay. So of course, in this Simpson-Maccabee-Thiele method, we have a similar story, that on a tray, the vapor leaving the tray and the liquid leaving the tray, they are in equilibrium. So these assumptions of the two streams in equilibrium still holds good, either it's a Maccabee-Thiele method or it's a Ponchon-Savarit method. All right. Except here, we make certain assumptions that this flow rate L is same as what we have getting here. Similarly, what vapor phase we have G here, molar flow rate, moles per second, is same as the tray underneath this. All right. So what is the basis of these assumptions? How does it evolve? From where do we get? Let's focus here. If you recall, in Ponchon-Savarit method, we had expressions for ln over gn plus 1. So the liquid which is leaving the tray n and the vapor which is arriving from n plus 1 or reaching this nth plate, the ratio of the two molar flow rate we wrote in terms of q dash enthalpy of the vapor phase n plus 1, and we had q prime over HLN. All right, which we can also write as 1 minus HGN plus 1 minus HLN over q prime minus HLN. So let's draw this schematic of this distillation column, and let's try to recall that we had the situations: vapor coming here, we had condensation. Let's say assume total condensation. We withdraw the product D, and the liquid goes back to the column as a reflux. So we had this x0 same as xd, all right, and we have the same as y1. So we have the total reflux, and we said that this q prime is nothing but the enthalpy of this leaving stream, taking into account for this QC here. So it's a hypothetical stream with a molar flow rate of D carrying a energy Q dash. So with that we came out with the expression. We said that if we choose any plate here N, then Ln, and we have this Gn plus 1. The difference between the two molar flow rate is same as D, and the difference between the energy of the two streams Ln and Gn plus 1 remains same as Q dash. So we had this differential point given as del T. Alright. So this is true with any envelope which we choose around the plate number n counting from the top. So we came these expressions and we can write like this. Now what happens that thermodynamically one can show that Hg n plus 1, so the enthalpy of the vapor arriving from plate number n plus 1. So this is what we have here, Hg n plus 1. So the plate n and we have plate n plus 1. Alright, Hg n plus 1 minus HLN, the enthalpy or specific enthalpy moles per calorie per mole of the vapor of the liquid leaving this plate N, which is HLN, is constant. One can show that this number is approximately constant as lambda m average. Alright, so this is the assumptions, first assumption we make here in this Machiavellian methods. Now every plates which we have in a stripping section or in the rectifying section, we have the stream, leaving, vapor and the liquid in the equilibrium, and the difference between the total energy of these two streams is same as Q dash. What we are saying here is that specific enthalpy Hgn plus 1, see the temperature varies from T1 to say T2 or Tn plus 1 to Tn. Alright, and this vapor and the liquid which are leaving, they are saturated with respect to this temperature. Similarly, this vapor and this liquid which are leaving the plate number n, they are saturated with the temperature T1. Alright, so although does the temperature change, but it doesn't change much, a lot. As a consequence, the difference between the specific molar enthalpy of the two streams, okay, one arriving here and one leaving here, is approximately, can be shown thermodynamically, equivalent to the latent heat of vaporizations multiplied by the molecular weight average. So although the molecular weight changes, why? Because the species mole fraction changes along the column, along the trace, but the product of this lambda and m approximately they remain constant. Why this happens? If we thermodynamically, if we recall from our previous calculations, we had the contribution from heat of solutions, right? If we neglect heat of solutions, which is actually true in the sense that kg per mole per kilomole of this quantity numerically, with what we call heat of solution, is actually much smaller. In fact, it's a one order of magnitude. So if you look at any handbook or thermodynamic table, you will see that this del Hs heat of solutions is one order of magnitude, say for example 10 to the power 2 kilojoule per kilomole, in comparison if you compare this with the lambda, latent heat of vaporizations. So although latent heat of vaporization will change with the temperature or with the compositions, etc., they more or less this quantity is very large, 10 to the power 4 kilojoule per kilomole. So this molar latent heat of vaporization. So first thing is that this heat of solutions, one, is much smaller than the latent heat of vaporizations, and number two, on the same note, sensible heat or specific heat due to the specific heat, Cp del T, etc., this is also very small. If we neglect temperature drop del T between two consecutive stages, we can neglect these two quantities in calculations of this Hgn plus 1 minus HL to show that we have a quantity lambda m which can be considered to be more or less constant. Alright, so with this assumption of Hgn plus 1 minus HLN being constant, you can see here that the ratios of Ln over Gn plus 1 can be assumed to be constant. Alright, so what we have here, we are saying that the ratios of Ln and Gn plus 1, it's more or less constant. Alright, That means if you look at one, it stays here N, and we have this molar flow rate of vapor Gn plus 1, and the liquid which is leaving this plate Ln, the ratios of these two Ln and Gn plus 1 is a constant here. Ratios. This comes out from energy balance. And in that energy balance, we said that the difference between HgLn plus 1 and HLN, specific enthalpy or energy here, is a constant. From this, we come to this conclusion that the ratio is a constant. And now, if you recall, we can make a molar balance between one plate and another plate, say N plus 1 here. All right. If we do this, we can also write that Ln Gn plus 1, it means the same as Ln n plus 1 over Gn plus 2, etc. So this is Gn plus 1 here. So we have the stream which arrives here is Gn plus 2, and then we have this Ln plus 1. So this ratio is also constant here. In other words, we have this conditions here. The ratios of liquid and vapor is constant, number 1. Number 2, if you look at any plate here, we have Gn plus 2 plus Ln. So if you look at this plate here, N plus 1, the molar flow rate of vapor is Gn plus 2, and the liquid which arrives here is Ln. So the same as the molar flow rate of the leaving streams, which is Gn plus 1 plus Ln plus 1. With this 1 and 2, one can show that L0 will be same as L1, will be same as L2, and G0 will be same as G1, will be same as G2, will be same as Gn. So this is what is Becker-Hille method all about. Molar flow rate is a constant. Let's try to understand what we are saying here. Okay, so what we started with, Ponchon-Severett methods. All right, we said that energy balance, enthalpy balance holds good the way we had. The difference between the two streams reaching or leaving the plate same as Q dash. Okay, that's okay. Then we said that we came out with expressions with Ln and Gn plus 1. So the molar flow rate of the liquid leaving the plate Ln, and the molar flow rate of the vapor which arrives at the plate N from N plus 1. We took these ratios in terms, we express this ratio in terms of Hg and Hgn plus 1. All right, HLN and Hgn plus 1. Now with that, Q dash is fixed. We came to the conclusion, or from thermodynamically we said that the difference between the two quantities, specific molar heat Hgn plus 1 and HLN, can be shown to be approximately equal to the latent heat of vaporization multiplied by molecular weight. So this quantity also more or less remains constant. Why? Because we very often we neglect the heat of solutions. It's one order of magnitude in comparison to latent heat of vaporization. You can look at the thermodynamic table given the textbook, Treball, or some physical handbook or thermodynamic handbook to convince yourself that this heat of solution is very often negligible. Similarly, it happens that sensible heat, recall your knowledge of thermodynamics or stoichiometry at some point, sensible heat is also very often is negligible in comparison to the latent heat of vaporization, which means from one tray to another tray, although the temperature changes, it turns out to be that the difference between the specific enthalpy of the two streams we are talking all the time, Hgn plus 1 and HLN, more or less this remains constant. If this is constant, one can show that the ratios of molar flow rates, Ln over Gn plus 1 is a constant. So we have two trays, N and N plus 1, or 1 and 2. So we talk in terms of Ln, L1, G2, then L2, G3. All right, we can always take the ratios of any plates in, say, rectifying sections. So if it's a constant, the ratio is a constant, and then you make this total balance. At one tray, you have two flow rates. One liquid gets here, and the liquid leaves here. So we have, say, L1, and then we have L2. Similarly, we have G2 and G3. You make a balance for these two. The ratios one can show, as I leave this as an exercise to show that even L1 individually, L1, L2, L3 will also be same. Similarly, G1, G2, G3 will also be same. Okay, so this is the foundation of your assumptions, rigorous assumptions. It sounds Becker-Hille methods. So far, whatever we did it in Ponchon-Severett methods, remember we had a suffix L1, L2, L3, L4, G1, G2, G3. to identify the source of these two streams or from which plate it originates. So the plate AN, we said we have Ln and we have Gn. Some other plates we said Gn plus 1 and Ln plus 1. But now because of this simplifications, we don't have to drop this suffix because all L's are same, all G's are the same. So it's a very rigorous assumptions, but it has certain thermodynamic foundations because of certain numbers, quantities like heat of solutions, latent heat of vaporizations, sensible heat. From this one can show that this approximation is not very far from the reality. It does happen, the trace temperature does not change much in the sense that two consecutive trays are more or less they are very close. So we can make these assumptions to result in the quantities like the ratios of two molar flow rates of liquid and vapor is a constant. Then we make a molar flow balance around the plate, 4 streams, to show that even the individual molar flow rates of the liquid and the vapor are the same. Okay. So with that assumptions, now we continue and we see that the similar whatever we got for this rectifying sections should also be holding good for stripping sections. All right. So what we did was we had this rectifying section. Let's note down what we did. So rectifying section, we took a plate here N. All right. We had this vapor Gn plus 1 and the liquid Ln. Here we had the plate say N minus 1. You can also choose N plus 1 here. So we had this Gn and we had this Ln minus 1. Now we are saying that Ln minus 1 is same as Ln and Gn plus 1 is same as Gn. All right. Physically, what does it mean? If we have 9 moles per second, let's see here. It's also 9 moles per second. If we have say 3 moles per second of the liquid here, we also have 3 moles per second. So how this is possible? Physically, all it means that whatever vapor has arrived here, say X number of mole or N number of mole condenses, this will also result in N moles of liquid vaporizing from here, so that the molar flow rate is conserved. So what we had so far was the ratios Ln over Gn plus 1. Then we made a material balance to convince ourselves that with this is as good as Ln's are constant, Gn's are constant. Okay. So physically what's happening? If you have 9 moles or 10 moles per second of vapor arriving here to this plate, which comes in contact with this liquid. So we look at this plate, vapor comes here and the liquid comes here. We have the pool of the liquid. Two streams, when they come in contact, the vapor will condense and the liquid will vaporize. So if we have 5 moles of this stream condensing to this, we have 5 moles of liquid vaporization. As a consequence, the molar flow rate will remain the same of these two guys and these two streams. Okay. So here it's very important that we understand the meaning of the physical meaning and physical interpretation of this Cavatili method. We are saying that molar flow rates are constant for the liquid and the vapor, but physically also it should be consistent with your mechanism here. So what's happening here, that whatever vapor we arrives at certain plates, it comes in contact with the liquid from the next higher stage. When they come in contact, the two streams, then if we have X number of moles condensed, right, then we have X number of moles vaporized, so that entire molar flow rates of the vapor as well as the entire molar flow rates of the liquid, they remain the same. That's the basis of your Cavatili methods. And in the word we can write here that rate of liquid overflow on molar basis is constant. On each tray. Of course, first we note that it's a molar basis. Not, we can make a note here that not on weight fraction basis or weight basis. All right. So liquid overflow as well as the vapor flow rate is constant on each tray. We can do the similar argument. We can have the similar arguments for stripping section. Alright, so even in the stripping section, if we choose a plate, say, we give the nomenclature, say M, and we have M plus 1, alright, counting from the top, then one can, we have the same argument here, that liquid which arrives here. So if we take a liquid which arrives to this plate and the vapor which arrives to this plate, when they come in contact, we have equal vaporizations. So whatever number of moles of vapor condenses to this, it gives rise to the same number of the liquid. So that's the physical meaning of this. These two streams are still in equilibrium, so that whatever flow rates we have, if we denote by L bar, and if we denote here, say L bar M, and here we have Lm bar M plus 1, the two will be the same, and molar flow rate will be the same. So similar argument here for the vapor, G bar M plus 1, and here we have G bar M plus 2, the two are the same. Alright, so we can also write here L bar. So bar here, it means this molar flow rates for this rectifying, for the stripping sections. Of course, you must make a note that L bar is not same as L. Molar flow rate in the two sections are different. Why? Because we have in between the feed entry. So they will be, we'll talk about this later in details, but L without any bar here, it represents rectifying sections, and L bar represents the molar flow rate for the stripping section. So L bar 1 or L bar 2, right, or M plus 1, M, etc., constant. Similarly, we have this G bar M, same as G bar M plus 1, equal to constant. Right, of course L bar won't be same as L, and G bar will not be same as G because of feed entry, due to feed entry. Okay, and here we have the same argument, the starting for the first principle, one can say that L bar M over G bar M plus 1 will also be constant. Alright, so now let's see what we have here in this HXY diagram. Of course, we said that we'll confine our discussion in this Macquarrie-Thiele methods on XY diagram, but here also we try to understand the physical meaning of this, the ratios of two molar flow rates being constant. So if we draw an arbitrary curve for HG and for HL, then we have something like this, HG and HL. Recall we had this vertical line going from this XD. Let's assume we have total condensation. We have this Q dash, alright, this line we drew, and we had this another line here which is Q double dash. We have XW. Okay, so if we draw all these operating lines like in the previous class, so first we had the one stage, we had the second stage, similarly we had this another stage here. So this stage 1, stage 2, stage 3, and all of this line we connect here to make this as an operating line. So the first number we put it as, say, G1 or HG1, then we had G2, then we had G3. Similarly here we had L1, L2, L3. So now we are talking of these ratios, and arbitrary ratios of Ln over Gn plus 1. So we said that this is approximately constant. Now when it happens here, so all we are saying that, say, L1 over G2, this is constant. Okay, and why this was constant? Because we said that all this quantity is same as Q dash minus H2 or Hg2 over Q dash minus H1. Alright, so if you mark all these points here, look at one vertical line this, and another vertical, this line like here for, say, G3, and here we had this L2. Okay, so this is what we are trying to say here, that this is Q dash minus this enthalpy. See this is a Q dash minus G3, right? or this enthalpy of this H2 here. Similarly, we have Q dash minus H2. Q dash minus H2 is the bigger one. So the ratios of these two segments is a constant for any stages which we can draw here. All right. So what happens, on the geometrically? Essentially, if we have the HXY diagram, and suppose we have this linear enthalpy between the enthalpy of the pure components. So 0, 1, if we draw a linear lines between G and H. In other words, we assume that the enthalpies of vapor and the liquids are linear, so and parallel. Okay, so they're linear and they're parallel, so the distance between the two is the same. And we draw this line which we have drawn as for Q dash. We're starting from xt, and we take another line here, an arbitrary line. One can show that the ratios, the segments which we are talking here, this segment and this segment will remain the same. Right. So even here we are trying to say that this is also consistent with the enthalpy. If the enthalpy lines or the vapor and the liquid is linear between the enthalpies of a pure components corresponding to the 0, x equal to 0, and the enthalpy of the other components, more volatile components, at x equal to 1. If we draw a linear curve between the two and the parallel Hg and HL, and we draw these lines starting from Q dash difference points and the several of these operating lines, and take the ratios, what we are talking L1 over G2, equated to the enthalpy difference between Q dash and Hg2 and Hg1, one can show that this is also consistent with the geometries. See, all we are trying to say here that the assumptions of equimolar flow rates, which we had, all L's are same, all L bars are same, G's are same, G bars are same. They came out from thermodynamic considerations, where we neglected the heat of solutions, we neglected the sensible heat in comparison to the latent heat of vaporization, which is a very good, assumptions here. All right. Based on that assumptions, we showed that the ratios are the same. Then we make the molar balance around a plate to convince ourselves that even the individual molar flow rates of the liquid in one sections and the other sections will also be the same. Similarly, the vapor will also be the same. Now we go back to this HXY diagram, and we understand the way we did it earlier classes, two examples we had. In reality, of course, these enthalpy curves, they're not linear. So there is a variations, it's a slant, concave downward or concave upward. But more or less we can draw a straight line between the two ends. In that case, this line will be more or less parallel and linear to the second line. So it's also a thermodynamic simplifications, but it's not very far from the reality. If you have gone through several examples given the Trebol book or the Datta book, the second reference book, you will see that more or less these enthalpy curves there are linear, or at least you can make that assumptions with a reasonably good simplifications. So if you make that assumptions of linear and then look at these ratios, it turns out to be that this is consistent with the thermodynamic criteria or the simplification which we obtained to say that ln over gn plus 1 is same as q dash minus hgn plus 1 and q dash minus ln, etc. All right. So we must understand here that although Macabeth-Thiele methods is a simple method, it sounds like a very rigorous assumptions, but it's not very far from the reality. And most of the times for practical design calculations, how to calculate the number of plates, condenser load, reboiler load, most of the people they prefer this Macabeth-Thiele method. It's easy to construct, it's easy to work on, unlike the previous methods, which is a very rigorously based on your enthalpy balance. Right. So we have the maths here thermodynamically, then we switched this to this geometry on HXY diagram. We showed that they are consistent with each other, and they are also consistent with our physical assumptions, that why the molar flow rates of the liquid and why the molar flow rates of the vapor are constant. Why? Because the number of moles of the vapor which condenses is same as the number of moles of the liquid which evaporates or vaporizes. So L bar is conserved, L is conserved, G is conserved, and G bar is conserved. So it's very important that before we take up an example, or we will see how we can construct this XY diagram, number of stages, theoretical stages, we keep our concept clear about the physics, about the thermodynamics, and about the geometry. All right. So let's continue with this. All we said that if we have this YX diagram, so now from now onward we are going to work on this y versus x diagram. So this is the 45-degree lines, and we have this y-x diagram like this. We are saying that because of that assumptions of L by G or L bar by G bar, constant C1, C2, if we have something called operating lines, then these operating lines will be linear. We will see how to construct this operating lines. So whether we have the operating line for this enriching section, enriching or rectifying section, and we have this line for a stripping section or exhausting section, then these two lines will be linear. Okay, and this linear, of course, just for the last time we say here that we are assuming that enthalpy balance and enthalpy of the vapor and the enthalpy of the liquid is a linear and they parallel. In reality, of course, it will be like this. There will be some slant, but it's a very good assumption. Okay, now with that introductions, now let's see how we can construct the number of stages. Let's see how we can do it with the simple example with this distillation column with a total condenser. So we have these plates here. The top plate 1, the vapor which arrives to this condenser has a molar flow rate G. So notice here that we don't have any subscript. Why? Because we said that all G1s, G2s, Gn is the same. So the molar flow rates of the vapor is G here without any suffix. However, it has a mole fraction which is 1, Y1, because the mole fraction will change as the rectification goes on. So now we have this condenser QC, vapor condenses, total condensate to give rise to this XD, and we have this reflux X0 with the flow rate L. Now again here we are not writing any nomenclature, any subscript for L, L0, L1, L2, L3, etc. for the same reason that the molar flow rate of the liquid in this section is also constant as L. So this reflux goes back to this distillation column with a plate. So we have Y1 and we have this X1, but still this is L and L. Plate 2 we have now Y2 and we have X2, but notice we just have L and we just have G. All L's are same here and all G's are same here, and it's a total condenser, so we have Y1 equal to X0 equal to XD. Molar flow rate is D here. All right, now we can do the same analysis which we did earlier. G1 which arrives here is same as L plus D, the reflux liquid, and the top product D here. The reflux ratio R is L0 over D, but always say this equals to L by D. Alright, so no subscript here, which means we can write this as D R plus 1. Alright, now let's take an arbitrarily stays here, say N. So the vapor leaving has a mole fraction Yn plus 1, liquid leaving this tray has mole fraction Xn. All we have just 1 G, and all liquid which we have here is L. No subscript here. Excuse me. So we are writing G equal to L plus D, D R plus 1. If we now make a total species balance, we have G Y n plus 1. Excuse me. So we have this Y n plus 1 here, and here we have just Y n. All right. So we are taking this envelope of this stream and this stream, Gyn plus 1 equal to L Xn plus D XD, and then we have Yn plus 1 equal to L over G Xn plus D over G XD. Alright. So now with these definitions, that G equal to D R plus 1, alright, it's not difficult to show that. Now we are obtaining Yn plus 1 equal to R over R plus 1. So we are writing in terms of reflux ratios. L by G, we have G equal to L plus D, and G also equals to DR plus 1. And here we have R equal to L by D. Alright, that means L by G is R by R plus 1 into Xn plus xd, and d by g will be 1 over r plus 1. Alright, so essentially we have got the operating line equations, which we can box yn plus 1 over r plus 1 xn plus xd over r plus 1. So that's the equation of the operating line in terms of reflux ratios, which is, you can say, or we obtain same as L over G. The ratios, internal reflux ratio, if we call it L by G, no suffix, that's more important. That's the Machiavellian methods. All L's are same, all G's are same. L by G constants xn, plus we have d by g xt. Alright, so either this or this. We have the operating line equation for rectifying sections. What does it do? Well, we have n here, so this is yn, this is xn, two are in equilibriums, that's a tie line. And what we have here is yn plus 1, between yn plus 1 and xn from the operating line, given by this equation or this equation. That's the operating line does it. It connects between the mole fractions of the two streams, leaving the liquid living here and the vapor arriving at plate. So we made that envelope to obtain these equations here. Alright, now we can go back to this xy diagram, and we can mark coordinates. So we have y and we have x. Recall we have this total condenser, so we have xd here, alright, and the vapor which arrives here is y1. This is x0, same as xd, same as y1. This liquid goes to the top column with 1. We have this y1, alright. Liquid which leaves here is x1, two are in equilibrium. We have y2, and so forth. Now let's see what we do on this xyx diagram. So if we start with xd, we are supposed to draw this operating line. Now if we put xd in this equations, you can show that yn plus 1 will also be equal to xd. Alright, that means this point of xd at 45-degree line, same as this y here, will satisfy this operating line. In other words, if you take this point here and take the intercept, it's the equation of a straight line, y equal to mx plus c. So c is the intercept. If you take the intercept at xd over r plus 1, right, and connect with this, you should be able to convince yourself that this slope m will be same as this r over r plus 1. In other words, you can take a intercept, you can take a slope here. When it intersects that 45-degree line, what coordinates will we get will be same as xt. So it's your convenience how do you draw this. So generally when you draw this yx diagram, instead of taking the slope here, it's more convenient to start from xt, take this intercept at the 45-degree line, you have y equal to x, mark the graph at r over r plus 1, same as L over G, connect with this point. This will become the operating line equations. Operating line for n reaching section. And we have this y equal to x equilibrium curve. So again, look at this. We have this y same as xt. First point which you locate here is your y1. So we are starting now stage 1, stage 2. The vapor which arrives here is which leaves this stage 1 and arrives to this condenser. We have this composition of the top product leaving xt, y1 same as xt. So we have y1 here. Let's mark this point. This y1 is in equilibrium with this liquid at x1. So we have this x1, and now we have this y2 connected by this operating line. So we have this second points y2. So we have the similar story. Tie lines gives us equilibrium. Two streams leaving the stage, they are in equilibrium, and the stream which arrives, this stage 1, and the leaves, they are in connected by the operating line. So again we start with xt, same as y1. So this line satisfies the operating line. As we said earlier, that if you take the slope of the operating line and start from the intercept, we will also reach this point y equal to x. But it's more convenient to start from the intercept xt equal to y at 45-degree line. Mark this intercept, connect it, you measure the slope, you will get the same slope as before. We have r over r plus 1. Alright, this is the intercept, which is actually xt over r plus 1. Alright, so we have r over r plus 1, the slope, and we have the intercept, which is xt over r plus 1. So we have this y2 again. Let's start. This y2 is in equilibrium with this x2. So we have this x2, again this x2, and now we have this y2, and so forth. So starting from this, now we can construct the stages. The first stage is 1, second stage is 2, this is stage 1, this is stage 2, and so forth. We have the stage 3, etc. Alright, this kind of constructions can also be done for the bottom sections. Right, so if we do x and if we have y here like this, we are starting from xw, and with the equation of the operating line, one can also obtain this. We can also have the number of stages here, this is stripping sections. So let us now focus on this stripping section. And here also we assume, we have the similar assumptions that the bottom column or molar flow rates are the same. So there is no suffix or our L bar. Of course, L bar is different from L because there is introduction of F here. We'll come back to this later when we make this molar balance for the feed tray. So all L bar is same, no suffix, and all vapor leaving the stage has G bar. Alright, so we can do the same thing. We can choose a plate M. So the vapor leaving is G bar. Liquid arriving here is L bar. The small fraction will be Ym. The small fraction will be Xm minus 1. We have M plus 1. This vapor is Ym plus 1. This liquid is Xm, but the same molar flow rate, no suffix here, G bar G. If you take this envelope with Xm and Ym plus 1 with the reboiler, where the stream has this molar flow rate, say W, and we have XW. Alright, so this goes to the last plate, which is NP. Now since we have this reboiler, this is YNP plus 1. So these two streams are in equilibrium, XW with YNP plus 1. Now if we make this balance here, for the species balance and the total balance, L bar equal to G bar plus W. So L bar equal to G bar plus W. So this is the envelope which we have made around this. And similarly we have L bar Xm as G bar Ym plus 1 plus W XW, and we can rearrange to write Ym plus 1 over L bar over G bar Xm minus W over G bar XW, which is same as L bar over L bar minus W. Xm minus W, L bar minus W, XW. So instead of G bar, we are writing it L bar minus W, because very often it's very difficult to control the molar flow rates of G bar. It's very difficult to control as well as to measure. So generally, most of the times in the distillation column, we have the data for the liquid. So we can write G bar as L bar minus W. Two are the same. That's our operating line. Notice this, that this ratio is also constant here. This ratio is also constant here. The equation of this line is also y equal to mx plus c. We have the slope as L bar by G bar. Compare this to the previous one when we had the slope of L by G. And now we have the intercept, which is negative here. W over G bar or W over L bar minus W. But again, notice if you put xm as xw, you should be able to get ym plus 1, same as this xw. All it means, this coordinate also satisfies, it lies on this operating line as well as on this 45-degree line, which means now we can construct this operating line for this stripping section without finding this negative intercept. So similar to the previous case where we said that either we take a slope and the intercept, or it starts from this xd and connect with the intercept, one can do the same thing here. This xw also satisfied equal to this ym plus 1 or yw, also satisfy this operating line as well as this 45-degree line. Alright, so the equation of operating line for this, let's rewrite here ym plus 1 as L bar over G bar, which is a constant, xm minus W over G bar xw. So with this slope of L bar by G bar, and from yw xw, because yw xw, this coordinate satisfies this operating line, we can draw this operating line. So this is the operating line for a stripping section. Again, make a note here that instead of this, suppose somebody starts with the slope and the intercept of this, which should be negative here, right? One will obtain the same line, but there's no point. It's rarely done like this, because we realize immediately that xw and yw, it lies on this 45-degree line as well. So if you put it here, we'll get the same results here. It's better to take the start from xw, yw at 45-degree line and take the slope of L bar over G bar to obtain this line here. Alright, now we can start construction of the plates in the stripping sections, the way we have done it for the top sections. So we have this y versus x diagram. If we start from xw, so recall we have this bottom product xw, and the vapor which arrives to the bottom plate at NP through this reboiler is in equilibrium. So if we extend this line, first coordinate which will we get is y NP plus 1. So this is y NP plus 1. Two streams are in equilibrium, y NP plus 1 and xw. xw and y NP plus 1, they are in equilibrium. So we have marked this point here. Now y NP plus 1, and here we have liquid x NP. They are connected by the operating line. So first, if you have xw, and then we have drawn this operating line by the slope of L bar by G bar, this will give us x NP. All right. Again, extend this. We have the second vapor compositions y and p. All right. If we extend this, we have now x NP minus 1 and so forth. First stage is of course the boiler, which we have done in case of Ponchon-Chevrolet method as well. So we have boiler, then this stage is NP, then this stage is NP minus 1, etc. Right. So we have been able to construct. We go from the bottom approach, NP, all the time tie lines, and we have this operating lines, tie lines, the operating lines. Similarly, we have done for this top sections to complete our construction here. Alright. So let us summarize today's lecture. We started with a new method, Maccabe-Thiele method. This method you must have realized by now, it's much simpler than Ponchon-Severett methods. Of course, there is a assumptions. We talked about that assumptions, thermodynamic assumptions that leads to this conclusion that all L's are same in the top sections, all L's are same in the bottom sections. All G's are same vapor flow rate in the top sections, all vapor flow rates are same in the bottom sections. With that assumptions, we made a species balance, we made a total molar balance, and we showed that the equation of the line for the top as well as for the bottom section is a straight line, y equal to mx plus c. The slope is given by L by G, and here it's given by L bar by G bar. Alright. So if we have the operating line, we have the equilibrium curve, y versus x. Instead of hxy equilibrium curve for the Ponchon-Severett methods, we can again restart the constructions for the both sections. So we started from xt. We realized that vapor composition of the plate 1, it's same as the liquid composition, which leaves the top product, total condenser. So from here there y1, then come to this first plate, y1 is the equilibrium with x1, we mark to the equilibrium curve, x1 with y2, we go to the second stage or go to the operating line, then the second stage, etc. Similarly, we start from the bottom composition, xw, draw this operating line either from the slope and intercept or from the slope and starting from 45-degree lines where we have marked this xw and yw. Make a note that yw is a hypothetical point. The composition of this vapor yw does not exist in the distillation column. It's just like the mathematically that coordinate of yw equal to xw satisfies this 45-degree line as well as your operating line. So it's easier to start construction from the 45-degree line, take a slope of L bar by G bar instead of looking for the intercept, which is negative in this case for the bottom column, and then take a slope. A similar thing we did for the top column. We start from xt at the 45-degree line and then draw the line of L by G. Right. So we can construct and the number of stages for the top column and for the bottom column. Next lecture when we meet, we will see that how we can locate the feed. If you remember in the previous class also, we had spent a time on this location of the feed tray from the enthalpy energy balance. Here also we'll make some energy balance for this feed entry and see that we can mark or we can come out with another operating line. We call it Q line. Alright, so we have one operating line for the top section, one operating line for the bottom section, and one we have this Q line, feed line. All three lines will intersect at one point.